So welcome to this session. So in this session we are going to discuss about a special chart called as Smith chart. So what is the application of this Smith chart and how to calibrate this Smith chart and how to calculate different parameters using this Smith chart. And so prior to that, so what is the use of this Smith chart? Just imagine when you are solving a problem for the calculation of input impedance of a transmission line. So we have a complex equation, right? Zn is equals to Z0 into ZL plus JZ0 tan hyperbolic function of gamma L divided by something will be there in the denominator also. That's clearly it is a complex calculation. So whenever we are substituting all those parameters, we require a complex calculation, a complex division as well as some trigonometric relations. Similarly, whenever we are calculating our simple parameters like gamma and Z0, there also complex calculations will be there, a complex division will be there and a complex multiplication will be there. Nowadays we have computers, calculators, etc., but in our olden days there are no such type of tools for the calculation of any complex multiplications, for doing any complex multiplications or division. So in those days a scientist called as Philip Smith, he designed one chart, he developed one chart based on the properties of a simple property of the transmission line for the calculation of many more parameters in our transmission line. So he developed one special chart, and that using that chart you can calculate input impedance without using any calculator. So we can calculate reflection coefficient, or we can calculate a standing wave ratio, we can calculate the stub location. So later I am going to explain what is stub. So we are going to design different transmission line structures. So using that simple chart without any computer or calculator. So that's why the basic knowledge of this Smith chart is very essential. And so we need to learn how to develop this Smith chart, or how Smith was developed this chart, and how to use this one for different applications. So in this session I will start how to develop Smith chart, and later I will explain how to understand this Smith chart, what is the properties of Smith chart, and then we will solve very simple problems based on this Smith chart. So what is the basic property of our Smith chart and how it was developed? Now Smith considered our reflection coefficient, voltage reflection coefficient parameter, and he manipulated that reflection coefficient slightly. Just you observe, a simple procedure will be there for that one. What is reflection coefficient? Gamma R is equals to ZL minus Z0 divided by ZL plus Z0. In our previous session I may use this gamma R as just gamma, voltage reflection coefficient. Here to a little bit to identify that one as a reflection coefficient, gamma R I am using, don't get confused, both are same. So gamma R is equals to ZL minus Z0 divided by ZL plus Z0. This is only the equation that what he took, he rearranged that equation. For that, just you take Z0 common from the both numerator and denominator. If you are taking a Z0 common from both numerator and denominator, this will becomes ZL by Z0 minus 1 divided by ZL by Z0 plus 1. This is the thing that what we have. As in our previous class we observed and we discussed that ZL by Z0 is always said to be a normalized impedance. Whenever we are dividing our impedance with the characteristic impedance of the transmission line, whatever it may be, that may be input impedance or load impedance, then it will be said to be the normalized impedance. This will be denoted with a lowercase z. That's I am writing this one as ZL minus 1 divided by ZL plus 1. So this is the parameter that what we have for our reflection coefficient in terms of normalized load impedance. Right, now what I do is just I will take this one as a combination of real and imaginary. This reflection coefficient is always an imaginary, right? So this is a complex number, so it will have a real part as well as imaginary part. That's why I will write this gamma R as gamma real plus J gamma imaginary, which is equals to ZL minus 1 divided by ZL plus 1. This is the thing that what we have, right? Now this gamma real and gamma imaginary, I will once again take this one as gamma R plus J gamma I. Here R stands for real, I stands for imaginary, which is equals to ZL minus 1 divided by ZL plus 1. Now simply apply component and dividend rule on both sides. Just here what you have is that in the denominator we have 1, right? So apply component and dividendo, that gamma R plus J gamma I plus 1, that numerator plus denominator divided by numerator minus denominator. Here what we have, here also numerator plus denominator, ZL minus 1 plus ZL plus 1 divided by ZL minus 1 minus of plus 1 is minus 1. Now which is equals to, on the right hand side what we have, ZL will be here, so 1 will be cancelled, it is 2ZL divided by, here ZL will be cancelled, minus 2, which is equals to minus ZL. So here by applying the component and dividend rule, that what we have is this is the term which is on the left hand side and this is the term which is on the right hand side. But once again observe, what is the type of our load impedance? The type of load impedance is always a complex load, right? That may be a pure real sometimes, or a combination of real and that's a imaginary. That's if you are taking a capacitive or inductive, or the combination of resistive and capacitive, resistive or inductive, then this will becomes a complex load. If it is a complex load, how this will be written? Simply this will be written as a resistance part R plus jx with a negative sign in front of them. Then why I am taking this one as R plus jx and this R is a lowercase r, x is a lowercase s? Because this load impedance is a normalized load impedance, I will consider this one as a normalized resistance and I will consider this one as a normalized reactance. So clearly this small r, a lowercase r always indicates the normalized value, clearly remember that, and a lowercase x always represents a normalized reactance. Now this is the equation that what we have, gamma r plus j gamma I plus 1 divided by gamma r plus j gamma I minus 1, which is equals to minus of r plus jx. Once again I am saying that this r is a normalized resistance, x is normalized load reactance, right? Now what he did is just he took this real part and imaginary part. On the left hand side we have one complex division that he solved that one and he equated the real part of the right side with the left hand side, imaginary part of the left hand side to the right hand side. So these two he manipulated. After that one he got a value for r. You see, if you are taking the real part on the right hand side only, you will have r, that is in terms of gamma r and gamma I, right? Similarly on the right hand side we have an imaginary part, that is nothing but the reactance x, and this x will be equated to the left hand side. There also what we have is gamma r and gamma I. So you will get to two equations, so one is for r, another one is for x in terms of gamma r and gamma I. So not only that one, he manipulated those two equations. So he got pure equation of r, a pure equation of x, and he rearranged those two equations to get an appropriate form. Now directly what I do is just I will give you those equations because the analysis is not useful here. I will give you those two equations and I will tell how to analyze those two equations, how to interpret those two equations, and from those equations how we will get Smith chart. I will explain. So now what I do is just directly I will write down the two equations which are meant for r and x. Now after rearranging those two equations, that's which is meant for r and x, we will get these two equations. The Smith obtained these two equations after rearranging r and x. Now just observe what these two are. This is an equation which is in terms of, or which is in the form of x minus h whole square plus y minus k whole square is equals to some r square. Just clearly observe these two equations. This equation resembles x minus h whole square plus y minus k square, which is equals to r square. Here also it is x minus h square plus y minus k square is equals to r square. Now what is this equation? This equation is simply a family of circles, or a single circle if you are taking a constant for h, k and r, right? So this is an equation of a circle with center h comma k and radius r. Similarly we can say that the above equation is a family of circles, that I will name this one as equation 1. That equation 1 is a family of circles for different values of resistance, a normalized resistance. And what is the radius of this one? For equation 1, clearly what is the radius? Radius is equals to 1 by 1 plus r, right? This is the radius that what we have. And what is the center of the circle? The center is simply h comma k. Where is h here? R by 1 plus r comma 0. This is the center that what we have. So here clearly you can observe an infinite circles. It's not a single circle, an infinite circles for different values of r. For each circle you have unique radius and unique center point. If you are taking r is equals to 0, you may get one center and one radius. If you are taking r is equals to infinite, since r values are only for 0 to infinite, you can take the maximum value as infinite. For r is equals to infinity, you will observe one center and one radius. Now what you have to do is you have to draw all those circles. Starting from 0 to infinite, you have to draw all those circles on a sheet. So this is the first step that what you are supposed to remember for equation 1. Similarly, consider this one as equation 2. Now for the equation 2, you have a second family of circles. Radius is, what is the radius of our second equation? 1 by x. So the radius of our second circle is 1 by x and the center is simply h comma k. H is 1 and k is 1 by x, right? Here also this is not a single circle. What you will have is an infinite circles. For different values of x, starting from 0 to infinity, that is a positive reactance for L, that is inductive load, or negative reactance for capacitive load. This is so what you can say is minus infinity to plus infinity. So if you are varying this x value from minus infinity to plus infinity, you can find it's an infinite radius and infinite circle, and each will have their unique radius and center. So if you are drawing all those circles, once again you will get the family of circles. Now what you have to do is take the circles which are meant for R. Equation 1 is only meant for resistance. So these two are meant for resistance, that what you can say, and these two values are meant for reactance. So for resistance circles, what you have to do is just you have to take these two and calculate the center, radius, draw the circles. For reactance, consider these two, calculate the center, radius and draw the circles. Now embed the resistance circles on the reactance circles. For your understanding, what I do is just I will consider very simple points, the extreme points I will consider. It's for both resistance and reactance, and now I will give you on the board. So what will be the maximum limit of our circle, right? So here before that, what you need to remember is, so where we have to draw the circle, that's we have to draw the circle on a graph sheet. So whatever it may be, that may be resistance circle or reactance circle, that we have to draw on a graph sheet. That graph sheet will consist of an x-axis and y-axis. On the x-axis what we have? Gamma r, right? For both we have gamma r on the x-axis, that is the real axis, that's what you are supposed to say, and gamma I, imaginary axis, on the y-axis. By considering gamma r on x and gamma I on y, you are supposed to draw all those circles. So by considering these values for the extreme one, just I will draw only one circle for you, and remaining I will explain with the help of a very good chart. Now what we do is just we will observe also how to draw these circles for different values of r and different values of x. So what I do is just I will consider, as I said, I will consider only the extreme values or some of the important values, and for that I will draw the graph, right? Now what I do is I will consider the family of circles for r, and these are the center and radius for r. Now for different values of resistance, you don't take that r as radius or some other thing, resistance. For different values of resistance, so what is the center and what is the radius, that what I require, right? For clearly initially I will consider for resistance is equals to 0. If I am taking resistance is equals to 0, what is the center for that one? 0 by 1 plus 0 is 0, always 0 will be there, 1 by 1 plus 0 is 1. So for a 0 resistance circle, the center is 0 comma 0, radius is 1. So what I do is now I will try to take a graph sheet, and on the real axis I will consider gamma r, on the imaginary axis I will consider gamma I. I will try to draw the first circle, that what we observe now. So for that let us take, so this is the graph that what I am considering. On this graph, gamma r corresponds to the real axis which is on x-axis, and gamma I on the imaginary axis. Now for this one, draw the first circle. What is the center of the circle? The center of the circle is located at 0 comma 0. So this is the center of the circle, that what we have with radius 1. So let us take somewhere here we have 1, here also we may have 1, here we have 1, and we may have 1 here. So 0, 0 as center, 1 as radius. If I draw a circle, an approximate circle may be like this. This is one. Don't take that one as any other shape. This is a circle. If you take a compass and draw that one, this will be very easy to understand, right? Similarly, what I do is I will consider a random value r is equals to some 1. If I am considering r is equals to 1, resistance is equals to 1, then what will be the center point here? 1 by 1 plus 1, this is 1 by 2, comma 0. And what will be our radius? 1 by 2. So here what you are supposed to do is you are supposed to draw one more circle on the same graph sheet with different radius and center. Now what will be the center now? 1 by 2 comma 0. Where the 1 by 2 comma 0 will be? Somewhere here 1 by 2 comma 0 will be there, right? This is the point where we have 1 by 2 comma 0, and this is our 1 by 2, and this is also 1 by 2. So if you are drawing a circle with 1 by 2 radius, that will passes through these 2 points. So the circle may looks like this, right? So clearly this circle that what we have drawn initially is meant for r is equals to 0. Once again I am saying, don't take that r is equals to 0 as radius, resistance. R here always stands for resistance. For resistance is equals to 0, that these are the values of center and radius, and this is the maximum circle that what we have. And for resistance is equals to 1, the radius now was reduced, right? And the center varied, the center is shifted. Now if you are considering r is equals to infinite, let us take r equals to infinite value, that is a positive only will be there will be no negative. Then what will be the value of our center and radius? If you are considering an infinite here, just it's directly it is not solvable, so it's not solvable, so take r common from that one, then you will get here 0 comma 0 or 1 comma 0, right? What we get is 1 comma 0. So here what you will get is 1 comma 0 as the center point, and if you are considering r, or if you are substituting directly r here, 1 by infinite is 0. So for a resistance value of infinite, this will be the center and this will be the radius. So whenever we are considering a radius of 0, clearly you can say that it is a point, right? I have to draw this one now. At 1 comma 0, just you put a point. This is our 1 comma 0, right? So at this I am placing a point. Now at this one r equals to infinite, right? Now clearly observe. So in between, if you are considering, that is in between infinite and 0, if you are considering any value, the circle lies between this circle and this point. So within that particular circle only you have to draw all those infinite circles, right? Here I am not going to draw all those, just you need to imagine. So between the values of 0 and infinity, if you are taking any circle and drawing, then always there will be lies between that gamma is equals to 1, r is equals to 0 circle, right? That these are all called as the constant resistance circles. Clearly remember those names. Terminology is very important here. Along this circle always resistance value is 0. Along this circle always resistance value is 1. At this particular point resistance is infinite. So along those complete circles resistance value is constant. That's why they are called as a constant resistance circles. Now for the constant resistance circles, where the center lies? The center lies on real axis, right? Initially the center is here. Later for some other value the center moves to this location. Later the center moves to this location. So whenever in the competitive examination it was asked, clearly you need to tell that the center for a constant resistance circles on Smith chart lies on real axis or gamma r line. That what you are supposed to say. So this is a simple analysis for our resistance circles. Similarly we have to go for the reactance circle also. But for the reactance what you will have is as a positive value as well as negative value. Now I will consider the positive value for reactance. For x is equals to 0, so there will be no positive 0 and negative 0, so only one value will be there. For x equals to 0, now consider this equation. For reactance, what is the center? Just you observe here. For x equals to 0, the center is 1 comma 1 by 0 is infinite, right? So 1 comma infinity is the center that what we have, and what is the radius? Infinite. So you are supposed to take the center point on a line or at 1 comma infinity. 1 comma infinity means somewhere here will be there 1 comma infinite, and with the infinite resistance, if you are drawing infinite radius, if you are drawing a circle, that circle approximately goes to this particular line. So this is very important. You are supposed to remember, for x is equals to 0, 0 reactance, always the circle coincides with the gamma r line. This is one of the important points you need to remember, right? Now I will consider x equals to 1. Initially positive reactance I am considering. Then what will be the center now? 1 comma 1 by 1. Just it is 1 comma 1. 1 by 1 is 1. So with this center 1 comma 1, you need to draw a circle with radius 1. 1 comma 1 will be somewhere here, right? So with this center, and if you are considering 1 as radius, this is radius 1, this is also radius 1. If you are drawing a circle, that particular circle will move through these 2 points. Here I am not drawing the complete circle because it's the part that what I am going to draw at this location is unnecessary, right? So this is only the circle that what I am drawing to understand that clearly this particular circle is meant for x is equals to plus 1. So if you are considering the reactance value as 1, so this is a circle that what we have. Now what I do is I will consider x is equals to minus 1 also. If you are considering x is equals to minus 1, then what will be the center? 1 comma minus 1, and what will be the radius? 1 divided by minus 1 is minus 1. Don't say that minus 1 is the radius. Always the radius is positive quantity. It is 1. So with 1 comma minus 1 center, 1 radius, you are supposed to draw one more circle. So 1 comma minus 1 somewhere will be here. That is the center for our new circle, a negative reactance circle. And this is radius 1 and this is also radius 1. So if you are drawing a circle, then it goes to or it touches these 2 points. Now this particular circle is meant for x is equals to minus 1, right? Clearly with this particular step you can conclude. So whatever may be the values of x which are positive, they lie above the real axis. They lies above the real axis. So whatever may be the values of x which is negative, they just below the real axis. So here in our Smith chart, the upper part or the real above the part of our real axis, so this can be useful for a positive reactance, and below this one, this can be useful for negative reactance, right? Just you remember that one. For always a horizontal line will be there in our Smith chart. Above the horizontal line, positive reactance. Below the horizontal line, negative reactance. Positive reactance stands for inductive load. Negative reactance stands for capacitive load, right? So don't leave here. Go for infinite also. So x equals to infinity. That's what I am considering here. So for an infinite value, 1 comma 1 by infinity is 0. So 1 comma 0 is the center. 1 by infinity is 0. Right? Once again, for an infinite, this may be either positive infinity or negative infinity. Don't bother about that one. That I will consider as plus or minus infinite, which implies 1 comma 0 as the center, 0 as the radius. So you got the same point here. So 1 comma 0 is the center. Here you are supposed to represent about a circle with just 0 radius. Then it is a point. So x is equals to infinity at that particular point. So just what I did is I gave you very brief introduction about the Smith chart. So with the help of these equations, we defined different parameters and later we obtained different circles for R and X. I have drawn all those circles there. Now with this one, you can observe few points. Whatever may be the resistance circle that lies within this particular maximum circle that what we have drawn for R is equals to 0. That's why we will consider the Smith chart up to that particular circle only. Within that R is equals to 0 circle only, the Smith chart will be considered. For different values of R, you may get circles like this. For different values of X, not for R. For different values of X, you may get circles like this. For different values of R, you may get circles like this, right? Now observe, it's all those circles, that the circles which are meant for R, the circles which are meant for X are meeting at a particular point, that is 1 comma 0 on real axis. And yet this particular point, R equals to infinite, X equals to infinite. R equals to infinite, X equals to infinite means what? Let us consider ZL. ZL is equals to R plus Jx, which is equals to infinite plus J infinite. It's infinite. Infinite means what? Completely it was opened. That's why this particular point is always said to be point of open circuit. Here the impedance is just infinity. That's why this point is always said to be the point of open circuit. Now what about the opposite point exactly that we have here? Exactly here, this is called as point of short circuit. So for the point of short circuit, what may be the value of R and what may be the value of X? For this particular point, the value of R may be 0, right? Since it is a point of short circuit, so R is equals resistance is 0, X is also equals to 0. Yes, it is satisfying. At this point, the circle which is passing through is only R is equals to 0, therefore R equals to 0, and this is our X equals to 0 line, therefore this point is said to be point of short circuit, right? So this is a simple method how to draw the Smith chart and how to observe different circles. Here you are supposed to remember few points, that whenever we are observing the Smith chart, the complete circles which are drawn or observed on the Smith chart are meant for resistance, and the partial circles that what we have are meant for reactance. And then in the reactance also, positive reactance will be there, negative reactance will be there. The positive reactance always lies above the horizontal line, the negative reactance always lies below the horizontal line. Now we have many properties to this Smith chart. We can calculate many more parameters using this one. This is not only useful for transmission lines, this will be useful for calculation of our microwave parameters as well as antenna parameters also. So remembering the properties and understanding those properties is very, very important to solve any problem using our Smith chart. Now what I do is, I will show you the Smith chart, and each by point I will explain, so what are different parts of that Smith chart, and how to identify different impedances, and how to use this particular chart as admittance chart, and how to get different parameters from this chart using a simple Smith chart.